you very much. Our final talk is Professor Annemarie Friedrich. She is from Augsburg University, where she holds the chair of computational linguistics. Before that, she was a senior expert in natural language processing at Bosch Center for AI, and she is basically working on language understanding, on semantics, logical reasoning. And today she will be speaking about neurosymbolic models of uncertainty and logical reasoning. Please, the floor is yours, Annemarie Friedrich.
Okay. So last year I attended ACL in Vienna, and there Ed Hovey, who is a very pioneering NLP researcher, said that LLMs are like beautiful cars that occasionally kill someone. And the research in my team that I will talk about today looks at what happens when we use those cars to drive through a very bumpy surface. So basically if you go to a very complicated reasoning scenario, where it may not be the best car for this landscape. So we don't only probe the models and say, okay, this and this doesn't work or something like this, but we also implement neurosymbolic approaches to find alternative ways to overcome the reasoning problem. So the neurosymbolic approaches still use LLMs, so a car, but they add certain devices that we know are really good with reasoning. And this is nothing new. This has been very traditionally used and developed in computer science. In this case, it's symbolic solvers. So what does the LLM do? The LLM is for translation. We take a textual input and translate it to a logic programming language in this case. And we know that LLMs can be very good with translations because this is the task transformers were originally designed for. And then, so the symbolic solver can take over actually navigating the bumpy surface and doing all the complicated reasoning. In this case, it's the mathematical part of the reasoning. And then you can also feed this back if you want to call this like an agent system or something. That's what the terminology evolved, but it has already also been called neurosymbolic systems for quite a while. Okay, so why should we care about neurosymbolic models? First, LLMs. We know that LLMs cannot always generalize, but sometimes they can, but we don't really know when and when not. We do know that LLMs do not generalize as we humans do. So Dan Roth, who was also in the same panel session last year, said that before the conference he asked an LLM, like some state-of-the-art commercial model at the time, to write a short paragraph about himself. And the LLM described him. He's a famous professor, and said, okay, he won these and these and these awards. And he said, okay, well, the problem is he didn't win any of those. So the question is now, does this mean that the model didn't generalize properly? He said, no, actually it did, because typically famous professors have won a lot of awards, right? So the problem is that in contrast to humans, the models do not know when to generalize and when not. So like advocates of the opposite direction, of just saying, okay, we just need to scale models and use more parameters, use more data to train them, would say, well, ultimately the human brain is just a neural network. So do we really need symbolic reasoning? But we also know that something is still missing from LLMs. And just speaking from experience with my own brain, there comes a certain point in logical reasoning where I can do it, but only with a piece of paper and a pen. And so I think there's some kind of symbolic reasoning that we maybe might operate in different ways, but I think we will see what the future will bring on this. Yeah, the whole bug with this, speaking from the current NLP community, is that we actually don't know the extent of generalization of LLMs for sure, because now all the scientific studies have this problem of data contamination. Yeah, so in sum, LLMs may be okay for certain lookups, but a big question is that do we really want to trust them with decision making? And in this talk, I will show one path and argue that neurosymbolic models can actually add back the trust in the reasoning part of the problem. Okay, so one limitation with this neurosymbolic approach is that LLMs are not very good at translating to programming languages. Why? Because they take the data from GitHub, what are the most prominent languages there, C, Java, Python, but not a lot of people still write Prolog or answer set programming and so on. So the less data they've seen, the worse they are at translating to this language. So no large-scale training corpora exist. So I want to focus in, do a little bit of a deep dive in one work that we did. We built a data set that we called QUITE for quantifying uncertainty in natural text for training and testing neurosymbolic models. So we started out with a set of Bayesian networks that we collected. And then we have scenarios, so like, okay, do you want to give a certain person an insurance contract or not? So the data set always consists of several premises. So like if the insurance holder is a senior who generally avoids risk, there's a 90% chance that they have received a senior training, for example. So in practice, in our actual data set, these are much longer and have more variables. We also experimented with what happens if there's not a percentage given, but just a so-called word of estimate of probability as more close to how humans speak. Then we sampled observations from the graphs and expressed them in natural language, such as the driver has attended a senior driver's training and the car's mileage is something and so on, and also added questions. And from the original graphs, we could compute the accurate probabilities. The writing into natural language happened using templates, LLMs, and manual verification. But then also my PhD students spent a lot of time actually creating gold standard symbolic representations. This language is called Problog. It's an extension of Prolog where you can add probabilities to certain rules, basically. Okay, so what can you do with them? A lot of people these days take this data, feed it into an LLM, and directly take the probability. That's our baseline, yeah? And in addition, we apply a semantic parsing step where we get this symbolic data out of it. And semantic parsing is not actually a new research field in NLP. This is what I've been always working on. Yeah, not just now it's called, I don't know, natural language understanding or neurosymbolic models. Before that, it used to be called semantic parsing and has a really, really long tradition. And once you have these representations, the symbolic solver solves the mathematical part of the task. To improve this translation step, we also fine-tuned the LLMs. And of course, this translation step is not automatically verifiable. Yeah? So this is a black box model. We can't do much about this step. But if the translation is correct, and this is something that any human who knows Problog can, of course, verify, then we know here is where the bumpy reasoning part actually starts. We can actually say that the reasoning has to be correct then. So how well does this work? So I looked at I call it the Sherlock Holmes factor of LLMs, because Sherlock Holmes has to apply a lot of different reasoning types. You could have causal reasoning, where you have given a cause and deduce the likelihood of an observation. So for example, it's raining, so the street must be wet. You could also have an evidential type of reasoning. The street is wet, so it must be raining. But there's a third type. This is called the explaining away scenario. You have an observation like the street is wet, but you also know that your neighbor has just cleaned the street. So you know that the likelihood of that it's actually raining decreases because you already know the cause. Yeah, so how well did this work? At the time, we ran a few models, and I ran a few recent open weights models in addition. So what we found at the time was that, interestingly, GPT-4, the best model at the time, was okay with causal reasoning. If you say that solving 60% of the puzzles is okay. I mean, there's still headroom, I think, for LLMs on these difficult reasoning tasks. But it really dropped a lot for evidential and explaining away reasoning, and maybe that's because they are trained in a causal way. And when we use our relatively small, this was a 7B model that translated this and the symbolic solver, we achieve a performance that is consistent and doesn't matter like which reasoning type you look at. And of course this makes sense, because once you translated your problem, the solver doesn't care what type of reasoning is happening here. And I think it's very interesting to look at this from this side, because we also learn something about how LLMs reason. So before this talk, I was thinking, okay, how do more recent models do? So I ran Qwen 2.5, one of the best instruct models, open models from like a little time back, the time before the dataset release, actually, I have to say. And that one actually seemed to have improved on the other types as well. And then the current open weights, one of the open weights models that work best with a chain of thought was Qwen 3.6, and that actually got better, but it was after the dataset release, so I would take these numbers with a grain of salt. So a different type of reasoning problem we looked at was in the context of complex combinatorial search. And here, our goal was to generate valid programs that we can judge stepwise, but this time without the tedious manual work. So these kind of problems are assignment problems. In our case, they were posed in natural language, and we had the solution, but only the problem and the solution, and not the intermediate steps of the reasoning this time. So in this case, you have a team, and you want to distribute them over different roles in a software programming project. So these are, like, all the hints are constraints, and you can apply them basically in any order. So yeah, then you have, in the end, an assignment, like who is the architect, and there's some constraints on what skill can fill what roles, and so on. Yeah, so a nice property of answer set programming, or ASP, is that every constraint further narrows the set of possible answers or possible assignments. Yeah, it's a logic language. You end up with a lot of possibilities, whom to assign where, and then every statement narrows this down. And we used basically this interesting property of this programming language to automatically label data in a solver standard way. So we ask an LLM to sample program continuations, always like the next line of code. And then we can ask the solver actually directly. First, the solver will tell us, is it even syntactically correct? And it's often not in the beginning. And then it can tell us if the gold standard answer is in this current answer set. And then we can label our program continuations and use this data for either supervised fine-tuning or direct preference optimization, or whatever algorithm you want to apply. And this turned out to work pretty well. So in this paper, we used Llama 70B and Qwen 32B. Only LLM reasoning could only solve 20 to 30% of the puzzles, and a fine-tuned model actually worked pretty well with Llama to solve 60%. And then we also added an inference time reward, which is basically during inference giving a few more hints. In this case, it was from the solver whether the answer set actually decreased with the next step, because you might not want to generate a line of code that doesn't do anything to the program, because then it's likely not correct. And that actually was, interestingly, quite effective with Qwen. However, I also would like to point out with these difficult reasoning problems, like the state of the art on this data set is about 70% or less. And so I think there's still AI research to be done. Okay, so to sum up, I think looking into these reasoning problems, not just by running LLMs, but also by building neurosymbolic models, is interesting, because it allows us to build systems that are much better at complex reasoning tasks. Also, as I've shown, this can help us to gain insights in the reasoning strengths and weaknesses of LLMs. We showed that solver-in-the-loop methods actually can support LLM reasoning effectively. But I also think that future research is needed on actually which reasoning problems can be simply solved with model scaling. Yeah, so which ones just bigger models, although it may not be that environmentally friendly. And then actually how can we identify the problem type? Because I've shown two different approaches where we once used probabilistic Bayesian reasoning, and in the other hand, we used assignment problems. So in your AI assistant, maybe you want to identify which type of problem you even have and then run your specialized agent. Okay, and I'm personally also a linguist, so I think modeling actually the linguistic part of the uncertainty and how this interacts with model calibration is a strong interest of mine, and I think that also needs more attention. So if you're also interested in these topics, I would be very glad to meet many of you at the speakers' lunch, and want to thank my collaborators, and also feel free to add me on LinkedIn. Thank you. Okay. Dann sagen Sie noch mal was.
Well, this concludes our session. Thank you very much for coming. As Annemarie just said, we will meet all the speakers up there in the lounge. Please give all 4 of them a warm hand again, and let's thank them for their very engaged presentations here.